Yeah, okay. So this is an equation that we need to solve using Cauchy residue theorem, CRT. Okay. So now, firstly, I wrote it as f of z. Okay. This is the function we need to find the value of, and as you can see, it is not analytic at minus half, 0, and minus 2. Firstly, we got the circle z is equal to 1, right? Mod of z equal to 1. So everything within this circle that is from 1 to minus 1 should be analytic. If it's analytic, then the function ka value is 0. If not, then we need to find the residue about those points. Firstly, let's look at z is equal to minus 2. If you see this point, it's outside this region. No? We only consider all values inside this region. So we are not bothered by this. Now next, if you look at z, if you see it's right in the middle of our circle or our region. So we need to consider this one. So this is one pole. So for our poles, z equal to 0 is one pole, and another pole would be z equal to minus half. Okay. Another pole is z equal to minus half, which is about here. Yeah. Okay, so now to solve it further, we need to find the residue of the function at these 2 points. Okay. So for finding residue at z equal to 0, we basically use this formula. Limit z tending to 0, f of, what do you say, z minus z naught. So z minus 0 into f of z. F of z is this thing, no? Yeah. So we just write that down. 2z minus 1 upon 2z plus 1 into z plus 2. As you can see, this is basically z, so this and this gets cancelled, and now we just need to put z equal to 0. So up there in the numerator we'll get minus 1, here we'll get 1 into 2, so half. So if we call this residue as r1, we get our first residue as minus half. Nicer. Then for the next one, we find the residue at z equal to minus half. For that, our residue becomes limit z tending to minus half. Now we'll be multiplying it with z plus half, because minus of minus plus. Oh wait, sorry, z minus half. Hey, yo, why minus? Minus of minus plus only, correct. Z plus half only. So z plus half into our function. However, if you look at our function, we have 2z plus 1, no? So we need to reduce it so that it becomes, what do you say? We need to reduce it in such a way so that we can cancel this term out. Only then we can put a limit minus half. For that, if you look at this term, if we take 2 out common, then we should be able to cancel it out. Let's have a look. Z tending to minus half, z plus half into, if we take 2 common, we get 1, 2 here, and we get z plus half again, and we get z plus 2 and 2z minus 1. If you see, this term and this term now directly cancel out, and now we can put z tending to minus half here, correct? Also this is minus. Yeah. So now when we solve this further, we basically substituting this here, so we get minus 1 minus 1 minus 2 in the numerator. This 2 in the denominator will cancel with that, and if we put minus half here, we get 2 minus half, which is basically 3 by 2. Hey, also we forgot a z over here, no? We'll get 3 by 2 into minus half. So these two minus signs will cancel. This will become 2 into 2, 4. So we'll get 4 by 3 as a residue at point z equal to minus half. Nice. So this is our second residue. Now, in order to find the value of this integral, which we can call I, the value of our integral I is equal by this thing. What do you say? Cauchy residue theorem. Okay. So by Cauchy residue theorem, nice. Our residue comes out to be 2 pi I into sum of residues at all poles. Basically, these points are called as poles. Okay, z equal to minus half, z equal to 0. Basically, poles are points at which the function is not analytic. So sum of residue at all poles in region. It should be inside the region, no? So we get 2 pi I into R1 plus R2 basically, which is R1 plus R2, which becomes 2 pi I into minus half plus 4 by 3, which will give us 5 by 6 here, which reduces down to 5 by 3. So 5 by 3 pi I. Therefore, the value of our integral is 5 pi I by 3.